All right, hello everybody. Welcome back. Today we're going to be doing section 4.3. We're going to talk about logarithms, logarithmic functions, see what they look like graphically, all that good stuff. Let me pull up the slides and let's get going. All right, so section 4.3. Come here. There we go. Here's the overview. So we're going to recall or start by recalling an important theorem that's going to help us understand that there is an inverse for exponential functions, that an inverse actually exists. This important theorem, which we talked about earlier on in the course. Then we're going to get a definition for a logarithmic function. We're going to do a lot of examples of inverting these two functions. Then we're going to look at the graph of log base a of x. We'll talk briefly about graphing transformations of logarithmic functions. Again, it's just going to be the same thing that you saw back in chapter 2, except now applied to logarithmic functions. We're going to talk about the domain of a composition with the log function because that comes up a lot. We're going to talk about the natural and common logarithm functions, and we'll finish up with manipulating equations that involve logarithms. All right? So first, an important theorem to recall. You might remember this from back in chapter 2, I believe. If f is strictly increasing or strictly decreasing, in other words, strictly monotonic, then it's 1-to-1. And if it's also continuous, then it has an inverse. All right. This is one of the reasons why I was emphasizing the difference between strict increase and decrease and not strict increase and decrease, right? So if you remember these graphs of these exponential functions are continuous on the real numbers, and they are either strictly increasing or they are strictly decreasing, right? So what that means is that there must exist an inverse function for any exponential function. There must exist an inverse function, right? The existence is guaranteed because of that important theorem that we just recalled. So because we know that there exists an inverse, we give it a special name. We call it a logarithm, okay? So you can basically think of this in this way. A logarithm is like the exponent in an exponential function. Um, Quick little note here looking at these graphs. This is one of the reasons why we don't include the graph, or the function 1 to the x as an exponential function, because this graph doesn't pass the horizontal line test, right? It fails the horizontal line test miserably. In fact, it fails it as poorly as you possibly could because it is a horizontal line. So because this fails the horizontal line test, that means it has no inverse. This is one of the reasons we explicitly require that the base of an exponential is not equal to 1. Because if it were equal to 1, then that would not be an invertible exponential function. So we exclude that. All right. So this thing that is not an exponential function. All right, so what is a logarithm? So a logarithm of base a, where a is greater than 0 and a is not equal to 1, is denoted by log base a of x, and it's defined as the inverse of the exponential function of base a. In other words, this, if and only if this. All right. We're going to focus a lot on this relationship in just a minute, but before I move on to that, one thing I want to re-emphasize, I know I emphasize it a lot in this course, but this is just function notation. So you really want to be comfortable with function notation. This is just the name of the function, but because the function is so special, it's the log function, we give it its own special name. For most intents and purposes, this is just f, right? And this is the output of the logarithm base a function. So just remember, this is function notation going on, not multiplication or some weird thing like that, all right? Now, because the logarithm is defined as the inverse of an exponential, this is the relationship that it obeys. In other words, y equals log base a of x if and only if a to the y equals x. And we're going to emphasize this relationship a lot in just a minute here. One thing I want to point out, the domain of the log function is 0 to infinity. That's explicitly because the range of the exponential function is 0 to infinity. And if you remember, inverses switch domain and range, right? So the domain, I'm sorry, the range of an exponential function was 0 to infinity. So the domain of its inverse is 0 to infinity. Okay, now let's talk about this inversion relationship. Here's one example right here. 3 equals log base 7 of 43, 343 if and only if 7 cubed equals 343, which it does, right? So this equivalent statement here is just saying you can go back and forth and it's equivalent. This symbol here is pronounced log base A of X. A little notational note. A lot of times we will omit the parentheses that you see here and just write log base A of X like this, just because things can get a little bit cluttered and just to save us a bit of the visual clutter of having parentheses and parentheses and all these other things, okay? Um, Another note about this notation that you're seeing here, this is not saying log a to the power of x. I know some students, when they're getting comfortable with this notation in the beginning, they think that this is some like exponential, that this is like a to the x. It's not. This is just saying log base a of x. All right. X is the input of the log function. That's really all it is. And the subscript a just tells us what base we're working with because these logarithms could be any valid base, right? So we need to kind of tell ourselves, hey, what base are you even working with there? In this case, it's a. All right. So that's the notation. Like I mentioned a minute ago, this is an equivalence relation. So what it means is that saying this is equivalent to saying this. They mean the same thing. All right, and vice versa. You can switch back and forth between those representations at will, and we're going to do that a lot in this section. And you'll do it a lot beyond, I'll say. Logarithms are really, really helpful. One of the reasons that we love logarithms is they let us work with exponents explicitly, even if we don't know what the exponent is. So the utility of the logarithm is it brings those exponents down into the playing field so that we can actually work with them, explore them, investigate them, and so on. So remember, like exponents, you can think of them as like indexing factors or like telling you how many factors you have. Well, what if you don't know that information? Logarithms let you work with that unknown variable with everything we've already learned before. That's the beauty of logarithms. Yeah, they let us play with our unknown exponents. All right. Okay, so more about this inversion relationship. If you want to convert between these two representations, it helps to say this phrase out loud. A to the power of y equals x. So I want you to say it out loud to yourself for a minute, and I'll show you why we're doing that. So a to the power y equals x. Okay, so the reason that we're doing that is we're going to want to convert between these two things. And if I want to convert from the logarithmic form to the exponential form, what I like to do is I like to say a to the y equals x. And that's what you get. So a to the y equals x. Boom. And actually, I'll say some of my students in the past would actually call this the snail method because it kind of looks like a snail if you draw it nicer than I'm drawing it right now. But it's kind of like this snail swirly looking thing, okay? So this is the phrase that I always find helps me convert between these two representations. Couple other things to notice here. No matter what, a is always the base in these representations. So here this is log base a. In exponential form, the base is a. The only thing that's changing here is the inputs and the outputs are switching, specifically because these are inverses of each other. So a to the y equals x. Over here, the input is x. Over here, the output is x. Over here, the output is y. Over here, the input is y. They're switching, right? They're switching back and forth. Okay, now we're going to do some examples. And let's see, how do I want to parse this up? Okay, we'll do this in pieces. I do want you to try these on your own, but let's split it down the middle. Let's do these first, and then then you can pause and then you can try to do these ones, okay? So here's what I want you to do. I want you to try to rewrite these logarithmic equations as exponential equations using that inversion relationship that we just talked about, okay? So let me throw up the thinker for a minute. Just think about what you're going to do for a minute. All right. Now maybe say something out loud that will help you convert. Okay. And try to work them all out, and we'll do them together in just a second here. Just do this side. Okay. All right. All right. Okay, here we go. So let's start with the first one. And I'm going to use that phrase. That phrase is what always helps guide me when I'm doing these things. So 3 to the y equals x. Oops, come here. 3 to the y equals x. Just like that. Now this one, 3 to the 4 equals 81. So this is equivalent to saying 3 to the 4 equals 81, which it does, right? 3 to the 4 is equal to 81. That's why this is an equivalence statement. These are saying the same thing in different ways. Okay, 5 to the x equals y. And then this one, 5 to the negative 1 equals 1/5, which it does. 5 to the negative 1 equals 1/5. That's why that phrase is so helpful, right? And that's how you're converting from log form to exponential form, okay? Now, let's do the next batch. So now I want you to try to do these ones on your own. I'll just throw the writer up right away. Try to convert these to logarithmic form. And my hint to you is to remember that the base is still the base. Doesn't matter which representation it is. The base is the base. What switches are the inputs and the outputs. Okay, now let's do it together here. Okay, we're writing it in log form. So the base is still the base. So this is going to be log base 1.2 of m equals 3. There it is. So what switched was inputs and outputs, but the base remained the same. Okay, this one is going to be log base e of 9 equals b. Okay, this one's going to be log base a of 24 equals 4. And then this one is going to be log base 2 of 8 equals 3, which it does because, right? Because 2 to the 3 equals 8. That's another way you can check, right? Just by using that phrase again. A to the power of this equals, oh, a to the, hey, come back, come back. There you go. A to the power of this equals that. There you go. And that's like the core of the whole section, that inversion relationship. Okay, here are the answers written out so you can compare. Pretty much identical to what I just wrote. Now let's talk a bit about the graph of this function, these log functions. So one, the domain is 0 to infinity because that's the range of a to the x, which I said earlier. In other words, this is the important part, the log function can only accept positive inputs. Okay, that's an important takeaway from this section. Whatever is going into this logarithm function, it's got to be positive. It cannot be zero. It cannot be negative. It has to be positive. The log function can only accept positive inputs. Now, on the other side of things, the range of the log function is negative infinity to infinity. That's because that's the domain of the corresponding exponential function. But you'll see on the graph in just a minute, the log function can spit out any real number, but it can only take in positive numbers. It takes positive numbers and maps them to any real number. Okay, that's the idea. Um, because logs are inverses of exponentials, the graph reflects around the line y equals x, as we're going to see right now. So if this is the exponential function right here, a to the x, then its inverse is log base a of x, which looks like that. And it's just being reflected around um, that line y equals x. Hold on one second. All right, sorry about that. Just wanted to leave myself a little note about something. Oh yeah, so let's talk more about the graph. So this is what the graph of the log function looks like when a is positive. I'm sorry, when a is greater than 1. So when a is greater than 1, this is what the log function looks like. It is strictly increasing. And in fact, the limit as x goes to positive infinity of the log function is positive infinity. It may be hard to believe just by looking at this graph right here, but this will keep going up and up and up and up and up to infinity. All right. It grows very slowly. This is actually why we're going to talk about comparing asymptotic growth and asymptotic behavior in chapter 5, because the log function does grow to infinity. It just does so really slowly. Yeah, very slowly. In this case, the y-axis is a vertical asymptote, and that's because the x-axis is a horizontal asymptote of the exponential function that corresponds. Or you can just use you can notice this by looking at the definition of an asymptote, vertical asymptote, right? As x approaches 0 from the right, this plunges down to negative infinity. So by definition, that is a vertical asymptote when x is equal to 0. That's a vertical asymptote. Now, if a is between 0 and 1, this is what the graph looks like, just like so. So now it's strictly decreasing. It will go to negative infinity just very slowly. The y-axis is still a vertical asymptote for the same reason as before. And that's it. So it's just kind of swooping down like so. Let's take a look at Desmos and explore these graphs a little bit here. All right, let me pull that up. Here we go. Nice. Okay. So in the previous section, we had looked at this graph. This is the exponential graph. This is the line y equals x. I've just got it plotted on here. And now this is the corresponding logarithmic function. So watch this. Boom. Let me zoom out a little bit. You see how it's just reflecting across the line y equals x again, because logarithms are inverses of exponentials. So that's why we are seeing that reflection behavior. And it doesn't matter what the base is, that reflection behavior is the same. So as I increase the base, you see that? Look at that reflection relationship preserved. It doesn't matter what the base is, right? Yeah, still reflecting. Notice here, as the base increases, the exponential functions blow up really, really quickly, right? The logarithmic functions blow up more slowly. So again, it may be hard to believe, but this graph will continue to increase, strictly increasing all the way up in to infinity and beyond, right? So it's just really slow at it, that's all. Okay, now let's lower the base down. Okay, watch. Ooh, check this out. Watch what happens when we get to 1, right? It's going to shallow itself out a bit. We're getting closer to 1. Watch what happens when we get to 1 itself. But yeah, there's some bases in there where they actually cross. All right. And then when we get to 1, boom. Okay, remember 1 to the x is 1 for any x. But if the base is 1, then the function is not invertible. That's why we don't treat 1 to the x as an exponential function. That's why the log graph disappeared, because, a vertical line is not a function of x. It fails the vertical line test as miserably as possible. So we cannot have a base of 1, because if we do, then there is no logarithmic function. There's no log function of base 1. But as long as we're not equal to 1 and we're still positive, everything's good. Pop. There we go. So this is what it looks like when the base is less than 1. There we go. Now, let me hide the exponential and hide this line just so that we can kind of look at the logarithm on its own. So this is what it looks like when the base is less than 1. And when it's bigger than 1, it looks like that. There we go. As it increases, you get that. Go back down, you get that, and so on. Doesn't exist. There's no log base 0. For the same reason, actually, because if b is 0, 0 to the anything is 0, and that's a horizontal line, so it's not invertible, so you don't actually have a log base 0. All right. Again, you can play around with this on your own. Just follow that link on the slides. Just get comfortable with what these graphs look like, and you'll get some more practice on the homework and such. All right, let's go back to the slides. Let's briefly talk about transformations of these graphs. I've just got one example because it really is just the same as what we've seen in the past. So you can try this one on your own. Try to graph this function. negative log base 2 of x plus 1 using transformations. So I'll give you a minute to think about it. Remember, you can pause the video and think about it. Okay. Now, say something out loud to give yourself that verbal feedback, and then try to sketch it. See if you can sketch that graph, and we'll do it together in just a moment. Okay. All right, let's do it together. So the parent function here is log base 2, and it looks like it's going to get shifted 1 unit to the left and then vertically reflected. Yeah, so shifted 1 unit to the left and then reflected across the x-axis. Just like we saw before, the asymptote is going to obey these transformations as well. So the asymptote is married to the graph in that sense. Originally, the vertical asymptote is at x equals 0. Now it's going to be shifted 1 unit to the left to be at x equals -1. So it'll look like this. Here's the parent function, log base 2 of x, shifts 1 unit to the left, and then we're going to vertically reflect, just like that. That's it. Noted, yeah. So the asymptote moved. This was like this, and then when we reflect it vertically, it looks like that. And there you go. So that's pretty much it. You'll get to practice that more on the homework and on the activity and such. Right. Now let's talk about the domain of a composition. The good news is that this isn't as difficult as maybe some of the more general theory we were talking about in chapter 2 in section 2.6. The main thing that we're going to use is we need to remember that log functions can only accept positive inputs. So I'll do this. I want you to try A on your own, and then we'll do B and C together. But if you want to try them, you're more than welcome to. But I want you to try to do A on your own first. So think about it for a minute. Now, say something out loud, maybe what I just said out loud, and then work it out. See if you can find the domain of capital F. Okay. All right, let's do it together. Right. The main thing to remember here, anytime you are trying to find the domain of a composition with a log function, is this. The log function can only accept positive inputs. So that means whatever is going into those parentheses, it's got to be positive. Okay. Here, this is what's going into the parentheses. So we need this to be positive, which means x has to be greater than -3. And that's it. So the domain of this function is -3 to infinity, not including -3, right? Now, the next one is similar. You just got to remember, actually, this is one of those times where we omitted the parentheses because it gets cluttered looking. What's going into this log function is the absolute value of x. Excuse me. So in order for the log function to be able to process this thing, it has to be positive. Well, good news about absolute value is it basically makes everything positive or equal to 0, right? It makes everything non-negative. So if we want this to be valid, we just need the absolute value function to be strictly positive. So that means everything is okay except for 0 itself, right? Absolute value of 0 is 0, but the absolute value of any other number is positive. So the domain of this function, the domain of h, that composition, is everything except 0. Everything except 0, and here it is written in interval notation. Okay, now let's do the more tricky one. So here we are actually composing that log function with a rational function, the rational function right there. So the rule is still the same. Whatever is going in to that log function has to be positive. So what we really need to know is when that function is positive, okay? It's a rational function. We looked at how to analyze those back in chapter 3 at the end. So we're going to use that technique here again. What we really need to find is the intervals where the graph of this function lies above the x-axis. Because whenever it's above the x-axis, it's positive, right? The outputs will be positive. So we're going to do a sign analysis, just like we did in in section 3.9. We're going to create a sign diagram. We're going to plot all of the zeros and asymptotes of this function, and we're going to test values in between to find where things are positive or negative. Here we go. So this function on the inside, it's got a vertical asymptote at 1, and it's got a 0 at -1. So I plotted, wait, do I have that backward? Hang on a second. Oh, I do. I have this backward. Hold on, hold on. 1 minus t. Sorry, these are reversed. This should be the vertical asymptote, and this should be the 0. My apologies. I'll fix that. There you go. -1 and 1. Yeah, there we go. My bad. I have this backward. Okay, so vertical asymptote when t is equal to 1, and a 0 when t is equal to -1. Luckily, that doesn't affect the sign analysis, but it is a little bit weird if you're trying to keep track of things. Okay, so I tested the number -2 in this function here, and when I plug in -2, I get a negative number. I don't care what the number is exactly, I just care about the sign. So the input here, this thing, is negative. The input of our log function, this thing, is negative here. It's positive on this interval between -1 and 1, and then it's negative again when you're greater than 1. All right? So in order for our function to be defined, we need our values to lie inside that interval. The domain has to be between -1 and 1. Oops, there you go, between -1 and 1. That's the domain of G, this composition. All right. Now, pivoting a little bit, we got to talk about the natural and common logarithm functions. So there's two very special logarithm functions, the natural logarithm and the common logarithm. The natural logarithm, as the name implies, is the logarithm with base e. Remember, e is the best base. E is the best base, and that is why we call it the natural exponential and the natural logarithm. You'll see why when you get to Calc 1. But log base e is the natural logarithm, and because it is so special, it gets its own symbol, ln. Let me zoom in just to emphasize it for a minute. So whenever you see the symbol ln, it means log base e. That's it. It's just a shorthand, nothing funny going on. It's just a relabeling. That function is so very special that we didn't just want to call it log base e. We want to give it its own name so everybody knows that we're talking about that very special function, natural logarithm. I'm going to butcher this pronunciation, but if I remember right, ln was chosen because it's short for logarithm naturel. I think maybe it's French, but this is the natural logarithm. So anytime you see this, just pretend it's log base e, okay? Now there's another popular logarithm called the common logarithm, and the common logarithm is just log base 10, okay? Many textbooks at this level, and in this course, I will say, whenever you see log on its own, it means log base 10. I have some notes about that right now, but if it's ever missing the base, for now, you can just assume that it means base 10, okay? Now, a note about that. Yeah, this is true in lower division undergraduate courses. A note about that. These are the notations we'll be using in this class. The common logarithm is called that because most of the world uses a base 10 system, a base 10 counting system. Most of the world does. So calling a logarithm with base 10 common is that's why we call it common. A logarithm that has base 10 is common. Now, that being said, like I've said a few times now, the natural logarithm is the quote best logarithm to use for math and science. And in later courses, what you find is that this notation, log, actually means natural log. Um, so this symbol meaning log base 10 is something that only lower division undergraduate courses use. And once you get a little bit more mathematically mature and you can understand why the natural logarithm is the best logarithm, that is the one that people just start calling log. You might also hear me just call it log because I just can't help it. Um, So just be aware that that convention will change as you progress through your math courses. Um, yeah, yeah, I'll just leave it at that. I'll leave it at, oh wait, one other thing I'll say is to try to be unambiguous, oftentimes I will just denote it as log base 10. But yeah, I'll leave it at that. Okay. Now that we have those, let's try to manipulate some equations that involve logarithms. So first one, I want you to try on your own. I want you to solve this logarithmic equation for x. And before before you get too far into it, let me warn anybody about this. We don't know properties of logarithms yet. So if you've learned about logarithms in the past and you studied things like properties of logs, like splitting up a product into a sum or a ratio into a difference. We're going to talk about those in the next section. We don't know those yet, so you can't use those yet. For these questions, you've really only got one tool, and it is that inversion relationship, okay? So when you are solving these, I want you to use that inversion relationship to solve them, all right? Okay, think about this one for a minute. Now, say something out loud, maybe that inversion relationship, and go for it. Try to solve that equation for x, and then we will do it together in just a minute. Okay, here we go. So there is one other caveat that I did not mention, which is this. Remember that the logarithm function can only take positive inputs. That means there are restrictions on our variable, restrictions on our solutions, right? So we need to state that outright. We need to state the restrictions on our variables before we even start solving. So that's what I do as my first step. The domain of the variable is 7/4 to plus infinity because we require that this input is greater than 0. So if you have this inequality and you solve it for x, you get x is greater than 7/4. So what that means is that any solution will only be valid if it's greater than one and I'm sorry, what is that? Yeah, 1 3/4. So we need our whatever our solution is to be greater than 1 3/4. Now we can solve. First step, invert. So we're just using that inversion relationship. Let me write it out again here. 3 to the 2 equals 4x minus 7. Boom. That's all I did. I just used the inversion relationship. Now we've got a linear equation. We've got a bunch of ways to solve that. Go back and use those old techniques. Go through the arithmetic, and you're all good. 9 plus 7 equals 4x. Divide both sides by 4. 16 over 4, so x is equal to 4. Because 4 is greater than 1 3/4, we're all good. That's a solution to the equation. Okay, now let's take a look at it on Desmos. Just like we saw in the previous section, right? Let me set this up here. There's a geometric interpretation of these solutions, right? Algebra and geometry, best friends forever and ever. Let's take a look right now. Okay, so here, yeah, here we go. That was example 4. Yeah, okay, let's take a look at example 4. Oops, come here. Okay, so what I've got graphed in blue is the function log base 3 of 4x minus 7. Here's what it looks like. Here's that vertical asymptote. Notice where the vertical asymptote is. It's at 1 3/4, right? And that's why we had that restriction on our variable. Whatever the solution is, it's got to be bigger than 1 3/4. And then what I have here is the line y equals 2. That was the right side of the equation. So the line y equals 2 is this horizontal line. Now, where do these two curves intersect? Right there, when x is equal to 4. And that's it. When x is equal to 4, this will be equal to 2. And that's pretty much it. That's it right there. All right, let's do the next example. Next example here. Yes, okay, this is an interesting one. And we're going to take a look at it in a minute here. So I want you to try this one on your own as well. So you're trying to solve for x still. So think about how you might do that. Right. Okay. Now say something out loud. Maybe just what you notice that's different about this equation. right? And now try to work it out on your own, solve for x. Remember, there may be restrictions on the variable, and then we'll do it together in a moment. Right. Okay. All right. Okay, we're all set. All right, so first and foremost, that variable is the base. That's the base of the logarithm. Might seem a little bit weird, but it's totally allowed. No worries, it's just a little bit weird, but we can totally do that, and that's not a huge problem. There is a restriction though. If you remember, the base of the logarithm has to be positive and not equal to 1. So that's our restriction right out the door. The domain of our variable is positive and not equal to 1, okay? Now we can solve. How are we going to solve? We're just going to use that inversion relationship again. So here, let me just trace it out. X to the 2 is equal to 64. Boom, right there. And now we solve for x. Remember, anytime you take a square root, you have to include a plus minus. You always have to include a plus minus. And then depending on the context, like in this question, you can remove one of those cases. So the solutions, the potential solutions are plus or minus 8. X could be plus or minus 8. However, our restriction specifically says that this has to be positive. So we can eliminate the negative case, and our only solution is x equals 8. X equals 8 in this case. Um, yeah, x equals 8 in this case. Let's see what it looks like on Desmos. Pull it up right here. There we go. All right, so this is the example we just did. Oh wait, is that, sorry, this should say example 5. Hold on. Do that now before I forget. That should say 5. This one should say 6. All right, save that here. Okay, example 5. So y equals log base x of 64, y equals 2, and then this is what it looks like. Okay, so in blue here, this blue graph that you see right here, that is the function log base x of 64. So that blue curve here, and there's this other piece of it right here. One thing I want to point out, notice that there's an asymptote at 1. There's asymptotic behavior when x is equal to 1. Because remember, x can't be equal to 1. The base of the logarithm cannot be equal to 1. That is why that is excluded from the domain of our variable. It's excluded. X can't be 1 in this equation, right? Then I have the line y equals 2. This was the right side of the equation. So where does the line y equals 2 intersect the curve y equals log base x of 64? Right here at 8. And that was the solution we had found, 8, right? Another thing I want to point out, notice that negative 8 is not a solution. You don't see an intersection over here. This graph doesn't even appear over here, right? That's why you have to consider the domain of your variable, because negative 8 is not an option, and 1 is also not an option. Those have been excluded because of the restrictions on our variable. Um, and it's a pretty interesting graph. So you can kind of look around at things. If you want to mess with it, you can. You can zoom in to see what kind of weird asymptotic behavior is going on there. But that's a solution. I mean, that's a picture of the solution. All right. Okay, one more example. Move that out of the way. One more example. Try this one on your own and we'll do it together. Think about it for a minute. Right. Say something out loud. Maybe ask yourself the question, are there any restrictions on the variable? All right. Now try to work it out on your own and we will do it together in a minute. Okay, here we go. So first of all, this is an exponential function. This is an exponential function. And any real number is acceptable to an exponential function, so there are no restrictions on the variable. It could be any real number. The second thing that I'm noticing here is that this is like this is the exponential function e. It's like the natural exponential function. It's not vertically shifted at all. And because the range of this is 0 to infinity, and this number is in the interval 0 to infinity, there's got to be a solution. And there will be one solution, just one solution. So that's the first thing to notice is that there will be a solution. 4 is in, remember that little symbol means in or is an element of. 4 is an element of that interval, 0 to infinity. So there must be a solution. Excuse me. Um, Same technique as before. We're going to write it in log form. So now we're actually going backward using that other part of the inversion relationship. So we're going to go backward in this sense. It's going to be log base e, right? So this is equivalent to log base e of 4 equals 2x, just like that. And that's what I got here. Remember, log base e is the natural logarithm, so I'm just going to relabel it as we prefer, which is ln. Now we're just solving for x, so I'm going to divide both sides by 2 and write it like this: 1/2 ln 4 equals x, and that is the solution. That's the solution. Another short little note here. For those of you that have already learned about properties of logarithms, we actually could simplify this a little bit more. Turns out this will be equal to log of 2, natural log of 2, but we're going to save that for the next section. Let's look at Desmos one more time just to see what this looks like and get a geometric interpretation, right? All right. So I've got my function here, y equals e to the 2x. This function here, y equals 4. Here they are. In blue, I've got the exponential, and then in red, I've got that horizontal line, y equals 4. Where do they intersect? Right here, 0.69315. And I'll bet you that that's about equal to 1/2 log 4, 1/2 natural log 4. Let's check. 1/2 ln4 is, so Desmos is approximating it as 0.639147 yada yada, and this is 0.69315. There we go. So it is actually picking up the same intersection point. That's where those two graphs intersect. All right, cool stuff. Now, on that note, you know what time it is. It's time to play. I hope you enjoyed this one. I'm always excited to work with you on this stuff. My team is always excited to work with you. So I hope you enjoyed this. And we've only got one more section left in this chapter. That's section 4.4. That's all about properties of logarithms, which are pretty cool. Okay, I'll leave it at that. Thank you all again for watching, and I will see you next time. Bye bye, everybody.